Hi everyone, today we're going to talk about relative age. So whenever we're looking at a cross-section of rock or a series of layers that are exposed to the surface, we can actually use a puzzle-like technique to piece together the relative age of those different layers of rock based on some rules that we're about to talk about. Now, a long time ago, nobody was really sure how old the Earth was or how it was formed, and there were two very fundamental theories that were being debated. One was called catastrophism, which was the belief that the world was created in a very short period of time due to many sudden catastrophic events. Now, of course, we know now that's not the case. However, for a long time, people thought this was true. The other theory is called uniformitarianism. And somebody named James Hutton disagreed with catastrophism. And he said the same processes that govern how the universe works now and how the Earth works now have always been the same. Therefore, the Earth must have been around for a very, very long time, undergoing very slow, gradual processes. That's uniformitarianism, and it's true. So before we talk about how do we look at different rock outcrops and compare them based on their age, we need to talk about some ground rules, pun intended. The first rule is igneous intrusions are younger than the rocks that they cut into. So if we have a whole bunch of layers of sedimentary rock and suddenly we have an igneous intrusion cutting into them, the sedimentary rocks must have been there before the igneous intrusion. This is called a cross-cutting relationship. Another rule, any fault through an existing rock has to be younger than that rock because the rock had to be there to begin with. Also called cross-cutting because one feature cuts through another feature. When sediments are deposited, they're deposited in horizontal beds, which means sediment layers further down are older than sediment layers closer to the top. This is called the principle of superposition. I know what you're thinking. These all have fancy names, but they're so common sense. It's true. Finally, if we have any small piece of existing rock that's been broken up and actually lithified into newer rock, that chunk of older rock is obviously older than the newer rock that it's just been incorporated into. This is called inclusion. Now let's take a look at this cross-section of rock. We have some folded metamorphic rock down here. We have an igneous intrusion, a couple of faults, some sedimentary layers, an obvious eroded surface, and a dike cutting through some of them. So based on this diagram, let's start by listing the features from oldest to youngest. So let's start further down in our diagram since that's where we're going to find the oldest rock. B is our igneous intrusion. Obviously, it's got to be younger than this folded metamorphic rock because it cross-cuts the metamorphic rock. B has to be older than this fault line F, but younger than the metamorphic rock. So let's keep that in mind. We have a couple of faults. Fault line F cuts through our igneous intrusion, it cuts through this eroded surface, and it cuts through these sedimentary layers. So it's quite young. It was formed fairly recently. Whereas this fault line over here, fault line A, only cuts through the folded metamorphic rock. Everything else cuts through it. Therefore, we can probably safely say the folded metamorphic rock is our oldest feature in this image, followed by fault line A, because it only cuts through the metamorphic rock. After fault line A, the next thing that cuts through fault line A and nothing else is actually the igneous intrusion, B. After that, every other feature cuts through the igneous intrusion. So far, we have folded metamorphic rock, fault line A, igneous intrusion, B. Now, at some point in history, there was some erosion that happened and actually wore down the metamorphic rock, the igneous intrusion, and fault line A, and then a whole bunch of sediment was deposited on top of it, C. Now, C has to be older than the eroded surface, but it's younger than this intrusion, which is a dike. It's younger than this new sedimentary layer, E, and it's got to be... So this sedimentary layer is newer than this eroded surface, but it's got to be older than this dike, D, older than this new sedimentary rock, E, and older than this fault line, F. So after our igneous intrusion B comes our sedimentary layer C. Next up, if we look at our layer at the top, E, the only thing that cuts through the sedimentary rock E is fault line F, meaning fault line F is the youngest feature. E is our second youngest feature. And if we take a look at the only other feature here we haven't labeled yet, D, we can say E is younger than D because E cuts across D. It's on top of D. So listing these out, hey, they're alphabetical. Our oldest rock is the metamorphic rock. All of the other features go alphabetically, ending with F, which is the fault. Let's take a look at this picture. So we have a nice big chunk of igneous rock. We've got a lighter felsic composition dike, and we also have a basaltic dike as well. Can we figure out where the rocks go from oldest to youngest? Well, we're going to have to use some cross-cutting because they clearly cross-cut each other. The youngest has to be the basaltic dike because it cross-cuts both other types of rock. Next up, we have our felsic dike. It cuts across this older original rock, but the basaltic dike cuts across it. So the middle-aged one is our pegmatite. And then finally, the original igneous intrusion has to be the oldest, and that's just using this term called cross-cutting. Now sometimes you will have a layer of rock that gets eroded, and then more rock, usually sedimentary rock, gets piled on top. That eroded surface is called an unconformity. Sometimes they're really easy to spot, sometimes they're trickier to spot, but that tells you that a certain amount of time went by. You probably lost some information, some rock layers, before newer rock was piled on top. Here are some definitions for different types of unconformity. The first kind of unconformity is called an angular unconformity. This one is fairly easy to spot. There are two different layers of different aged sedimentary rock. The bottom older layer is actually at a weird angle because originally the older layer was laid down horizontally, but over time it was uplifted and tilted. There was some erosion, so now there's an eroded surface, and then newer sedimentary rock was laid down in horizontal layers as well. The next kind of unconformity is called a disconformity. In this case, we have horizontal layers of sedimentary rock, erosion happens, and then newer layers of sedimentary rock are layered on top. This one can be a little harder to spot, especially if we're talking about very similar types of sedimentary rock. And finally, we have a nonconformity. Let's say we have an igneous or a metamorphic rock that's been eroded down, and then we have layers of sedimentary rock piled on top of it. That's a nonconformity. Here's an example of an angular unconformity. Here you can see older rock at an angle, an obvious erosional surface, and then some horizontal layers of sedimentary rock on top. Here's a picture of a disconformity. Here we have some nice horizontal layers of old sedimentary rock. We have an erosional surface here, and then we have new sedimentary rock laid down on top. Finally, we have a nonconformity. Here we have some nice granitic, an erosional surface, and then a completely different type of rock on top, sedimentary rock. In this image, we're going to treat this like a little puzzle, and we're going to figure out the relative age of all of these different labeled features based on what we know about cross-cutting and superposition. The different patterns represent different types of rock. So the limestone is represented as brick, dolostone is the angled brick, granite is the little flecks, sandstone looks like sand, and shale is the little horizontal lines. So what I suggest is try this on your own first. Try answering these questions on your own first, then come back to the video, and right now we'll talk about the answers. The first thing to do is to label the different unconformities. This example here is an igneous intrusion. So this squiggly line actually represents the edges of the igneous intrusion, whereas this squiggly line represents an unconformity. As you can see, the sedimentary layers below the unconformity are at an angle. The sedimentary layers above are horizontal. Therefore, this is an angular unconformity. What is the oldest rock shown? Well, it's going to be one of the layers at the bottom. If this is an igneous intrusion, it has to cross-cut these sedimentary layers, meaning these sedimentary layers had to be there before. So K, which is our bottom sedimentary layer, has to be our oldest rock, and it happens to be limestone. Now what we're going to do is use the labels to figure out what is youngest to oldest, and then we're going to list them. Note there are some that are ambiguous, so you might have a slightly different solution, which is actually totally fine. Like we said before, K is the oldest rock. Originally, all of these layers of sedimentary rock would have been laid down horizontally. Over time, they would have been uplifted and put at an angle. Now, this is an igneous intrusion. It cuts into our layers of sedimentary rock, so it's younger than all of these layers of sedimentary rock. K is the oldest. This shale, which actually goes up here as well, is the second oldest. E is a little bit younger. This limestone, a little bit younger, and G, a little bit younger as well. Now C is the next youngest because it cuts into all of these layers. Notice how this fault line cuts into the igneous intrusion, meaning it's younger than the igneous intrusion. This basalt sill cuts through the fault, so it has to be younger than the fault. We don't know whether the sill is younger than this unconformity or not. That's the ambiguity in this drawing. So you may have put something different, and that's totally fine. After some erosion happened, we had all of these horizontal layers of rock laid down. So layer H, the sandstone, the shale, the limestone, more sandstone, and finally layer I, which is our youngest layer. So here's the answer. Notice how the oldest to the youngest, there is some uncertainty about when exactly that sill was formed, because really it could have been formed at a couple different points in time. Last question. If you wanted to collect the oldest rock sample that you can access from the surface, which one would you collect? Take a look at the picture. Here's the surface. You can walk all the way down this surface. So the oldest sample that you can actually collect from the surface would be this igneous intrusion, which is labeled as C. Which sandstone layer was deposited at the same time as sandstone layer J? Here's sandstone layer J. It's part of the angular layers of sedimentary rock. The only reason it's up here is because it was shifted due to this fault. So J and E are actually the same layer. They were deposited at the same time. The only reason they've been shifted relative to each other is because of this fault line. So the answer is E. Here's another example that you should start by trying on your own and piecing together the clues just like it were a puzzle. Again, we're talking about the same legend, same different patterns for the different types of rock. E is going to represent some sort of folded metamorphic rock. In this example, we're going to start by labeling all of the unconformities. D is an unconformity, C is an unconformity, and so is B. So there's all three types of unconformities in this example. You may recall that a nonconformity is when you have igneous or metamorphic rock eroded down with sedimentary layers deposited above. That happens to be what D is. An angular unconformity is when you have sedimentary layers at an angle, eroded down, more horizontal layers of sedimentary rock deposited on top. So C is an angular unconformity, which leaves B. B is called a disconformity. Horizontal layers of sedimentary rock eroded down, and then more horizontal layers deposited on top. So those are our different unconformities in this picture. What is the oldest rock shown? Well, we have metamorphic rock eroded down with all of these layers of sedimentary rock deposited on top. Everything crosscuts E. Therefore, E, our folded metamorphic rock, has to be the oldest. Now we're going to go through all of our labels A through J and list them from youngest to oldest. Oldest is obviously our metamorphic rock. Next up, that metamorphic rock had to be eroded down. That's our first unconformity, D. Now, if we take a look at all of these different sedimentary layers, they had to be laid down next. Notice how A, which is this dike and sill formation, cuts across the metamorphic rock, all the sedimentary layers, as well as the unconformity. This fault cuts across the sill. Therefore, all of these sedimentary layers were there first. So F, and that's the only, and J. J is older than F. So J and F would be the next oldest and then youngest. After that, the sill and dike would have been formed. After that, this fault line G would have happened because it crosscuts all the other stuff. At that point, we have some more erosion, and C, this unconformity, was produced. Next up, we've got our layers of horizontal sedimentary rock. H is the only label in this central layer. Then B, we have another unconformity, more erosion, followed by more layers of horizontal sedimentary rock, which is I. So here are all of the features listed from youngest to oldest. Last question, which unconformities could you actually examine from ground level? In this diagram, you can walk all along this surface. So the only unconformities that you can examine from ground level are this one, which is our angular unconformity, and this one, which is our disconformity. We can't even see this one from ground level in this example. So can the techniques we just talked about be used to help relative date features on other planets and moons? Yeah, they can, because planets and moons are typically covered in craters, especially if they don't have a lot of geological forces acting on them. So the density of craters, which means the number of craters per unit surface area, can help us determine the age of the surface of a planet. Heavily cratered surfaces are typically older than surfaces that have fewer craters. Also, craters can be weathered away as long as that planet had some sort of erosional force, maybe a liquid or atmosphere or other things hitting on top of the craters, or ice that's causing turnover of the ground. Now, not only can we determine the age of different parts of the moon by looking at craters in a relative way, we actually have samples from the moon as well, so we can determine the actual age of these rocks. These were collected during the Apollo missions in the 1960s and 1970s. Now, even if we don't have missions that have recovered actual rocks from actual planets or moons, we can look at cross-cutting relationships between different features that exist on the surface of planets and moons. Here's a really interesting example from Mars. The first thing we need to do is define some different types of craters. They can tell us a story about the age of those craters. The first type of crater is a preserved crater, which means the rim of the crater is very, very clear and sharp. Sometimes you'll be able to see something called an ejecta blanket, which was just a result of some powder or earth or dirt or debris that was thrown off during the original impact. Some craters even have a central peak, not all. That often indicates the crater was pretty fresh, pretty new. The next type of crater is a modified crater. They've been changed or modified maybe by wind or water or lava. Maybe they've been cross-cut by other impacts. Their edges aren't as nice and sharp as a preserved crater, and they may be partially filled in. Finally, you can have a destroyed crater. These ones are almost completely gone. The edges are often filled in, the centers are filled in, and sometimes you can barely tell they're there. Now if we take a look at these craters. Crater A is a great example of a preserved crater. We can see a very sharp rim, and we can even see a really clear ejecta blanket. Crater B is a modified crater. The rim is fairly sharp, but not as clear as crater A, and you can see it's been cross-cut by other impacts. Crater C is a destroyed crater. The rim is barely visible, and the center has been mostly filled in. D is another example of a preserved crater, very sharp outer rim and a very clear ejecta blanket. In this next image, we have crater A, the large one, crater B, the medium-sized one, and crater C, the small one. And we're going to identify which one's oldest, younger, and youngest. The oldest one is clearly A. A could be described as a modified or destroyed crater. C and B cross-cut it. Now, if you look very closely at craters C and B, you will be able to notice that crater C actually overlaps crater B. So crater B is the middle-aged one, crater C is the younger one. And we know this because crater C actually cross-cuts crater B. The principle that we use to determine this is called the principle of cross-cutting. In the next example, we have this surface B, we have crater A, and we have channel C. The youngest feature has to be channel C because it cuts across both A and B. A cuts across B, so it is the next youngest feature, and B has to be the oldest. Again, we're looking at which features cross or cut in front of the others, which is a cross-cutting relationship.